Hello and welcome to day 11 of learning ML from chatgpt. Let's get started. So yesterday we learned about the the accuracy and the different ways of measuring how good the model is. So yesterday we also did the multi-regression, multi-class classification model in which we had to pass in custom arguments to the logistic regression from the Keras. Is it Keras? Scikit-learn. No, so it wasn't Keras. Okay. So we had multinomial as the multi-class. This was so that the logistic regression model knew. Then we had the LBFGS solver, and we had a custom iterations. We also had to change the macro average on this as it was giving an error. Oops, it was giving an error without it. So now I think it's convolutional neural networks with images, which is exciting. Okay. For some reason, hopefully my OBS has not crashed. Okay, I don't think it has. Okay, I'm just going to copy this. So please give me day 11's lesson. Okay, let's see what we're going to solve for today's lesson. Okay. So, day 11, convolutional neural networks, CNNs. Concepts. A convolutional neural network is a type of deep learning model commonly used for image classification, object detection, and similar tasks involving grid-like data. CNNs are particularly effective at capturing spatial hierarchies in images due to their specialized layers, convolutional layers, and pooling layers. Okay, so convolutional layers. These layers use filters, kernels, that scan over the input image, applying convolution operations to extract features like edges, textures, and patterns. A kernel moves over the input image and performs element-wise multiplication, producing a feature map or activation map. Okay, so we have these things called kernels or filters that find edges and textures. Then we perform some sort of multiplication on these, and they produce a feature map. Okay, I still don't understand it that well, but when we see an example, it hopefully make more sense. So pooling layers. Pooling reduces the dimensionality of feature maps, making the model more efficient and less sensitive to minor variations. Common types include max pooling and average pooling. So I assume this just goes over what the convolutional layer produced, and like we have for regularization, help remove noise. We don't become too fixated on certain minor variations, like it says here. Okay, activation function. ReLU, often used after each convolution to introduce nonlinearity. Okay. Fully connected layers. After the convolutional and pooling layers, the data is flattened and passed through fully connected layers, which makes the final classification decisions. Okay. So input layer accepts image data typically represented as a 3D tensor, height, width, and depth. Convolutional layers. 3D tensor, okay. So we don't just fasten it automatically like we did in the MNIST. Okay, so convolutional layers. Learn local features from the input. Pooling layers. Downsample the data to reduce complexity. Fully connected layers combine features and predict the output. Code example. Building a CNN in TensorFlow to classify images from CFAR 10. So we import the libraries, TensorFlow and Keras, so datasets, layers, models. We preload the CFAR dataset consists of 60,000 32 by 32 color images in 10 classes with 6,000 images per class. Wow. Okay. X-train or train. So it like the Iris dataset is very easy to split, and the MNIST. So X-test, X-train X-test equals X-train. So we're normalizing values to be between 0 and 1 as pixel image. Okay. So build the CNN model. The model consists of multiple convolutional layers, followed by pooling, then a fully connected layer. Okay, so we're doing model.add layers.convolutional 2D. Okay, have we already declared model? Oh, model.sequential. Okay, model.add layers convolutional 2D. So 32 filters. So this is like, I'm pretty sure filters is another word for kernel. A 3x3 kernel. Input shape of. Okay. So input. Oh, okay. So it's a 3-dimensional. Yeah, like it said before. Okay, input shape. First convolution. 32 layers. 3x3 kernel. Okay, I'm just gonna have to go with what ChatGPT says there, and then max pooling, reduce spatial. Okay, yeah, it said average pooling and max pooling were two common ones. 64 filters is the second convolutional layer. It looks like we're having the 2-2 pooling for each one. Okay, and both are activation functions. So this is doubling the amount of filters here. Then we're adding another convolutional network, which is also got 64 filters and the 3x3 kernel and the same activation function. Then we flatten it. Okay, and then we have dense layers. So these are the fully interconnected. And because it's softmax, so it's going to be multi-class classification. Okay, compile the model. We'll use the Adam optimizer categorical cross entropy since this is a multi-class classification problem and actually as a metric. Train the model. Train the model on the CFR train set for 10 epochs with a batch size of 64. Evaluate the model. Test loss. Test accuracy. Model.evaluate x test. Y test for both equals 2. Print F accuracy. Assignment. Task. Train the CNN on the CFR 10 data set and achieve an accuracy of at least 70%. Hint, experiment with different architectures, including adding more convolutional layers, changing the number of filters, or modifying the learning rate. Okay, so let's see this. As a 2D convolutional layer with 32 filters. Okay, so how do we go to 2D first off? When I'm pretty sure it said like 3D. Input layer. 3D tensor. How's it 2D when the input shape? I assume we're compressing it then into 2D. Okay, 32. I'm just going to ask it, please explain what this actually means. So what is a filter and what is a kernel? Because it's set up here, these layers use filters that can scan over the input image, applying convolution operations that extract features like edges, textures, and patterns. The kernel moves over the input image and performs element-wise multiplication. Okay, maybe kernels, a 3x3 was it looks at a 3x3 grid bit and finds like a edge or something in that particular part, and like but I don't get then what filter. Do they do it concurrently or do they like split it up? I'm just asking ChatGPT for the answer. Okay. Max pooling 2D. Create a max pooling layer with 2x2 pool size, reducing spatial dimensions. Okay. Oh, so I assume this is going from 3x3 to 2x2. Okay, that flatten patterns the 3D output convolution layers into a 1D vector, the fully connected layer, and we're having 2 dense layers. Output 10 neurons for 10, and softmax activation to output probabilities for each class. Okay, in convolutional neural networks, CNNs, filters and kernels are the key concepts used to extract features from images during the convolutional operation. A kernel, also known as a filter, is a small matrix, usually 2D, used to detect special features in an image. It is a size, e.g. 3x3 or 5x5. It slides, convolves over the input image, performing element-wise multiplication between the kernel and the input image at every position. Resulting values form a feature map. For example, with a 3x3 kernel might look something like this. Kernel detects vertical edges in an image. Okay, filter. Filter is essentially another name for a kernel. However, when we say 32 filters, we mean a layer that has 32 unique kernels. Each filter will scan over the image to detect a different type of feature, such as edges, textures, or patterns. In the context of CNNs, when we say 2D convolutional layer with 32 filters and a kernel size of 3x3, it means the CNN layer has 32 separate 3x3 matrices. Each kernel slides over the image, applying convolution, multiplying and summing up all values at every position. This operation creates 32 separate feature maps. Oh, okay. Each representing a different feature detected by the corresponding kernel. Okay. The result is a more abstract and feature-rich representation of the input image that the network can use to make predictions. For example, if your input image is 32 by 32 pixel RGB image, each convolution operation will produce a new reduced image feature map depending on the kernel size. There will be 32 of these feature maps, one for each filter. This is how CNNs detect multiple patterns and features in an image. Okay, I'm just going to ask it to explain So now please explain this code. Please explain all the different layers and what it does to the data. So my current understanding is that so kernels, we have here in the first line we have 32 kernels of 3x3, and each 3x3 matrix, it does some matrix multiplication, like it said, adding and multiplying, and we just go across the image until we've done it all, and it creates 32 different features, and then we perform all these on each feature, I assume, and then we can flatten it. And another question is, how do we combine all of the features that are made during that are made using all of the filters? Okay, let's see what it says. Okay, so code example. So it's just providing all of it. Okay, now it's doing it in the normal sequential way. Flattener, softmax, okay. Add optimizer. So input shape. Alright, 32, 32, 3. This reverses the shape of input images, of the input data images. Here the images are 32 by 32 pixels with 3 color channels, RGB. But how's it? The image with 3 color channels. But how does that make it 3? No, it doesn't. Okay. Okay. So it's not actually right. Each image is passed into the CNN for processing. 2D convolution layer. 2D. This is a layer that applies 32 filters. These filters will scan over the image to detect various features such as edges, textures, and patterns. Activation equals ReLU. The ReLU activation function is applied to each pixel in the feature maps, turning all negative values into 0, keeping the positive values. This introduces non-linearity, helping the network learn complex patterns. Input shape. This is the input shape, meaning each image is of size 32 by 32 pixels with 3 channels. Okay, output. The result of this layer is a set of 32 feature maps, one for each filter. Each feature map represents certain features the filters have detected in the image. Okay. Max pooling 2D. Max pooling. This layer reduces the size of feature maps produced by the previous conv2D layer. It does this by taking the maximum value of a 2x2 region of the feature map pooling window. Okay, so pool size it uses a 2x2 window region. Spatial size of feature maps will have the key being important features. Okay. So it's basically assigning weights to each little bit of the image, and then the highest one it keeps. So output, if your feature was a 32 by 32 before, after pooling it becomes 16 by 16. Pooling reduces the size, helping the computational efficiency and reducing overfitting. This is another convolution layer similar to the first one, but with 64 filters of size 3 over 3. This means that it will extract 64 new feature maps based on the already transformed pooled input from the previous lesson. Again, ReLU activation is applied. Output. After applying this layer, the CNN will produce 64 feature maps, these detecting more abstract and complex features. This pooling layer, again, reduces the size of 64 feature maps, but preserves important features. Similar to the previous pooling layer, this reduces spatial dimensions further. Output. If the feature map before this layer was 16 by 16, after pooling it becomes 8 by 8. Okay, but we had another one, so it becomes, would it be 32 plus 16? I don't know. So this converts the 3D feature maps into a 1D vector, so the data can be passed into. So if you had 64 feature maps with size 8 by 8. Oh wait. Oh, so it is converted to it. Okay. If you have the return of 64 times 8 times 8. Okay. This is essential before feeding the data into dense layers, which expect 1D inputs. Output. A long 1D vector that combines all the extracted features. Dense layer. Fully connected layer. This is a fully connected dense layer with 64 neurons. Each neuron receives input from all the previous 4096 values, the flattened vector, and calculates a weighted sum, adds bias, and applies the ReLU activation function. Dense layers allow the network to combine all the features detected by the convolutional layers and make sense of them for classification or other tasks. Output, a 64-dimensional vector representing a processed version of all features. Then 10. Dense layer of 10. This output layer has 10 neurons, one for each possible class in your classification task. E.g., if you have 10 classes like for 10, activation equals softmax. The softmax activation converts the output of each neuron into a probability between 0 and 1. The sum of all probabilities will be 1, so that the network can output which class is most likely for the input image. Output. The final result of the is a vector of 64 probabilities, where each value represents a probability of the image belonging to one of the 10 classes. Okay, when multiple filters are applied in the convolutional layer, each filter detects a different aspect of the input data, edges, textures. After convolution and pooling, the result feature maps from all features are combined through the filter flatten layer, converting them into 1D vector. This vector is then passed into fully connected dense layers, which combine the information from all feature maps to make predictions. In other words, Dense layers learn to combine all the features from different filters to determine the final classification. Each feature map represents a different aspect of the input data, and by combining them, the network can make more accurate predictions based on a wide range of visual cues. Let me know if you have more questions on this. Okay, I do have one question, and that is, so in this line are another 64. No, so in this line, you say that 64 new feature maps are created. So are these feature maps just 3 by 3, or are they the full image? Okay, let's see. In the line, let me clarify this. So 303 refers to the size of the small grid that slides over the entire feature maps. The result is the output of the convolution. The result of applying for a specific filter of size 3 by 3 across the input. So when you apply 64 filters, each of size 3 by 3 to an input image, or the output of the previous layer, each filter generates a full feature map, which is the size of the image, or its reduced size after pooling. So, for example, if the input into the convolutional layer is an image of size 32 by 32, each of the 64 filters will slide over this image, convolving it, and the result will be 64 different 32 by 32 feature maps, one for each filter. Okay. If the input is smaller due to previous operations like pooling, say it's 16 by 16, the convolution will create feature maps summary. The 3 by 3 is the size of the filter, which looks at small sections of the data. The 64 feature maps are the full output of the convolution process. Each one is the size of the input but represents different patterns of features detected across the whole input. Okay, I have one further question. I have another question. How are the 64 feature maps here different, as isn't the same operation being performed on them? Or is it that after every feature map is created, the weights and bias change? Okay, let's see. Quick question. Here's how the 64 feature maps in the idea. Each of these is by a different filter, also called a kernel. Each filter has its own set of weights and biases, so while the same operation convolution is performed for each, the filters are different. Oh, okay. Here's the breakdown. It has its own unique weights. These filters are small, e.g. 3 over 3, but their weights are initialized differently and are updated separately during the training. Convolution process. Each filter is slid across the image or the previous layer's feature maps. The filter performs the convolution operation, a dot product of the filter's weights in the image patch it slides over. This produces a feature map corresponding to that filter, which highlights specific patterns like edges, textures, or shapes. Weights and biases. Each filter has independent weights and biases, so after each feature map is created, it reflects the specific characteristics the filter has learned to detect. These weights and biases are learned during the training process. As training progresses, each filter learns to detect different types of features or patterns, e.g. edges or textures. Why they're different? Even though the operation convolution is the same, the weights and biases different. Okay, as a result, each filter detects different patterns in the input, producing 64 distinct feature maps. One filter might detect horizontal edges, another might detect vertical edges, one other might detect corners or specific textures. The 64 feature maps are different because they are generated by 64 unique filters, each with its own set of weights and biases. The same convolution operation is applied to each filter, but since each filter has different weights, the resulting feature map results highlight different aspects of the input. Okay, so that makes sense. I've got another question though. Where is it? Okay, I have another question. So after this layer, we have 64 new feature maps. So then in the layer after that, no, we have and then in this line, this layer, we have 64 feature maps. So what happens to the original 32 feature maps? Are the original feature maps do the original 32 feature maps also undergo the layer, or what happens? Okay, because this is the part I don't get. Here's how it works. When you apply the 64 after the original are not discarded, they're actually used as inputs for the next layer. Okay. Yeah, okay. So here's what happens step by step. The first convolutional 2D layer, 32 filters. In the first convolutional layer, conv 2D, 32 filters and kernel 3x3. You start with an input, e.g. an image with shape 32 by 32 by 3, where 3 represents the RGB channels. After the convolution operation, this layout has 32 feature maps. Each of these feature maps is a result of applying one of the 32 filters kernels on the input image. Second, convolutional 2D layer, 64 filters. When you add the second convolution layer, conv 2D 64, it takes the output of the previous layer, which is 32 feature maps, as input. Each of the 64 features in this. Each of these across the depth of the input is now 32. The filters perform convolutions, summing across all the. Why doesn't it produce 32 times 64 new convolutional layers, as these filters are operating on the output? Or are there only 2 new filters for each of the output feature maps? Are they feature maps? Yeah. Okay, how it works in detail. Input to the 64. The input to the second is now a 3D volume shape where 64. Each of the 64 filters are sized. This means that each filter covers the full depth, 32 channels, of the input and extracts features from all 32 feature maps. Output. After applying each of the 64 layers to the entire map input, you get 64 new feature maps as output. To summarize, the original 32 feature maps are not discarded. Instead, they are used as input for the next convolutional 2D layer. In the second convolutional 2D layer, each of the 64 filters process the entire set of 32 feature maps. The result is that you get 64 which combine information from the original 32 feature maps. Okay, I'll ask this question. Oh, that's not good. Okay, but that's not how it works. Let me explain in detail. Each convolutional filter in operates on all of the input features at once, but produces only one output map per filter. Here's how it works. Why? Let's assume you have 32 input feature maps from the previous layer, e.g. from... Okay, now you're applying 64 filters in the next. Each of the 64 filters in this convolutional 2D layer is a 3x3 in spatial dimensions, but in depth dimension, each filter will span 32 feature maps. Okay. I see. So each filter is now going on a 3D basis. I get it. So we have the 3x3 block. So you have like an image. So we have, say my hand is like, just like one feature map. Then we have maybe 3x3 at the like top bit here. But then it also goes all the way back there. So, like say it's a 3D and we have the 32 feature maps. So this would make a new 64 feature map. This is a 3D. And I get it. Let's go. This means each filter has a shape. The depth of the filter matches the depth of the input. Each filter combines information from all 32 feature maps into a single output feature map. This is done by performing convolution across the height and width dimensions and summing the results across the 32 depth channels. Output of the convolutional 2D layer. After each filter operates on the input, it produces one feature map. Since you have 64 filters, the result will be 64 feature maps, one per filter. The total number of output features will always be equal to the number of filters, not the product of input and output features. Okay, I get it now. So if you have 32 and apply all and combining information. Okay, so each filter in a convolution 2D layer produces one feature map, and it looks at the entire set of input feature maps together. This means that the number of output feature maps is controlled by the number of filters, not by the number of input feature maps. Okay, so now I'll just explain this because it's important. So I'll go back to this one. So at first we have a convolutional 2D layer. So we accept the input image, and we're doing this for every image in the like how many 60,000 images or something. It's crazy, something crazy like that. So we have the 32 filters. So these filters just create like each filter has a different set of weights and biases. So like for the first filter, we have a 3x3 it's called a kernel. This is a matrix. So we check each 3x3 and we go across and across and across and across all of the parts of the image. And then what we do is we transfer handles it, but it based on the weights and bias of the filter, which are all unique. So we want to have the same feature map that's produced. So in this one we have 32 feature maps produced because we're doing this like going through all of it, comparing 3 by 3 and calculating like values for each filter. So then after this layer we have 32 feature maps. Okay, and then what we're doing here is we're like halving the wait, so it says here max pooling. The layer reduces the size of the feature maps. Okay, maximum value 2D pool size. So if your feature map was 32 by 32 before, after pooling it becomes 16 by 16. Okay, pooling reduces the size, helping with the computational efficiency and reducing overfitting. Okay, yeah, so it halves it. So yeah, so that's what the pooling does there. And then this is the important bit. The second convolutional layer, we have 64 filters, but we have the same matrix. So what we do is we have, imagine a 3D basis. So you have the bunch of features, like all going back like here. We have the first one. Just imagine like you're doing on the first convolutional 2D layer. We have the matrix 3 by 3. So we check like the 3 by 3 section up here, but then this 3 by 3 section there not only applies to the first bit of, not only applies to the first feature map, but also it applies to the rest of the 32 feature maps. So then we can create a new feature map, which is the product of all like this part that goes back. So imagine a 3D perspective. So we're halving this again to make it, this would be from 32 by 32, 16 by 16. No, it wouldn't. It'd be 32 by 32 to 16 by 16, then 16 by 16 to 8 by 8. And then we're flattening this layer, and then we're having some interconnected layers. So we're having dense with 64 neurons, and that we're using 64 because that's the amount of feature vectors. And then the final layer is 10, and activation is relu again to introduce the nonlinearity. Then the final one is 10. We have 10 neurons, and the softmax function is 0 to 1, and that is well, yeah, all adds up to 0 to 1, and it gives the percentage like probability of it being that image. And then we compile it. Okay, I'm just gonna copy and paste this. I'm gonna do it at the top. Okay, so I'm just gonna copy paste this and ask it chatgpt to give the completed code. Okay, copy. So now with this, please provide the full completed code. I actually really like convolutional layers. It's hard to get at first, but the way they do it and like calculating the points, textures, I think that's really cool. Okay, just loading here. I don't know why it's doing model.add and it's not having the array of it. I think that's much cleaner rather than doing .add. It's a bit verbose and just unnecessary, but okay. We'll go with it. So Adam sparse categorical. Okay, so this is different to the binary cross entry that we were using before. So sparse categorical. I think this has something to do with the images because the MNIST, and I think we still use binary. But actually, we may have done sparse categorical. I can't remember 100%. Oh, this may take a long time. There's not much compute power we got for free on the Google Cloud. I don't know. It's definitely capped. Oh, look at how much that is. 170,000. Epoch 1 out of 10. Okay, let's see. Oh, okay, this is going to take a while. So I might have to pause the video or something. I don't know how to pause it. I guess I have to end the video now, and I'll come back when it's finished. So I'll try and add the 2 video clips together. Bye.